In this video, we present an alternative to the first derivative test. Now, if you remember, the first derivative test is a way of classifying whether a critical value is a relative minimum or a relative maximum. And the first derivative test is based on recognizing whether a derivative changes from a positive value to a negative value or vice versa, right? So that's where we did our nice little sign chart, and we observed in certain instances sign changes in f prime, and then we were able to conclude that at a specific critical value, a function has either a relative minimum or a relative maximum. Well, it turns out that the second derivative test in certain instances can also determine whether a function has a relative minimum or a relative maximum, right? To give you an idea of how that is possible, let's start with a sketch. It seems like all these ideas we start with a sketch, right? So here's our function y equals f of x. And I drew this function so that there are no sharp corners, but we do see a couple stationary points. So, roughly around here, the function has a relative maximum, and then roughly, say about here, the function has a relative minimum. Now let's take a look at what has to happen with the first and second derivatives for this to occur, right? Well, we know for a fact that to have a stationary point like this, the tangent line has to be horizontal, right? So we have to have a horizontal tangent line. And that means at this point, and let me just kind of indicate an x value there. So at that x value, I know that my first derivative would evaluate to 0. Right? So whatever the derivative of this function is, whatever this x value is, when I plug this x value into the derivative, I'll get a value of 0. I mean, that's part of our definition of a critical value. And similarly, at this point, again, whatever that x value is, let me just call it x1. Again, because the function has a horizontal tangent line at this point, right here, if I take my derivative and I plug in the x value that corresponds to that point, then I will get a value of 0, right? So that's nothing new, right? Because that, again, that's a part of our definition of a critical value. But what's new is this observation. Notice on this entire interval, our function is concave down, right? So on this entire interval, at every single point, the second derivative must be negative, right? So let me make that observation here. So on this interval, roughly to about here, f of x is concave down, right? So now that we have the notion of concavity, we're going to see how this property along with this property leads to this kind of critical value. Well, what do we know about when the function is concave down? Well, I just mentioned it. The second derivative would have to be negative. So that means at the same point, if I were to compute the second derivative of the function and evaluate it at the same x value, I would have to get a negative value. Why? Because the function is concave down, right? Concave down like a frown means your second derivative has to be negative. Similarly, look at what happens over here. On this portion of the graph, the function is concave upward. So again, roughly over here, our function f of x is concave upward. What do we know about concavity? Concave up, like a cup. And what that means for a second derivative is at every point in this interval, at every x value in this interval, the second derivative would have to produce a positive value, which includes this specific value. So if I now took f double prime and evaluated at x1, I would have to get a positive quantity. And what the second derivative test is, it uses both of these facts to get to this conclusion of a relative, let me write that over here, a relative max. So it's the same, we're talking about what happens at the same point. So if you have a critical value, specifically a stationary value, and the second derivative evaluated at that value of x, if you get a negative number, then it means that that critical value has to correspond to a relative maximum. Similarly, if I find my critical value, which again we've done quite a bit of late, right? We find our critical value, taking our first derivative and figuring out the values of x that make it equal to 0. If we figure out those x values, the way again we can test to see if we have a relative min or a relative max, find the second derivative of the function, evaluate the second derivative, and see if I get something positive. If I do, then the conclusion is that stationary value is a relative minimum, right? So again, this is a combination of our two derivatives. So we use our first derivative, as always, to find the critical values of my function, y equals f of x. But then I can use my second derivative to classify them, to tell the difference between having a high point or having a low point, right? Now, unfortunately, you might say, well, what happens if the second derivative comes out to be 0? Well, that's where we wouldn't be able to make a conclusion. So in other words, the second derivative test would be inconclusive. So I would need to do something else, maybe revert, go back to my first derivative test to figure out if we have a min, a max, or neither, right? So let's actually summarize that in the form of a theorem, and then we'll do some examples, all right? So let's see. So for this to work, in fact, let me write the name of the theorem, our second derivative test, right? Well, so the function would have to be twice differentiable. So obviously I'd have to be able to differentiate it twice. So let f of x be twice differentiable. So twice differentiable on some interval that contains, and I'll just use the x0 as my x, so that contains, so on some interval that contains x equals x0, right? If our first derivative evaluated at that specific value of x is equal to 0. So that means, again, that's one of our stationary points. So if the first derivative is equal to 0 at that point, and so here are the three possibilities. If the second derivative evaluated at that point gives me a positive value, then my original function has a relative minimum at x equals x0, right? So again, first derivative evaluated at that point is equal to 0. Second derivative evaluated at that point is positive. When those two things happen, the only possible conclusion is that that critical value is a relative minimum. In fact, that's the one we see right here, right? Second possibility is, well, maybe I plug into my second derivative and I get a negative number. Well, then this is what will happen. We'll have to have a relative maximum. So then f of x has a relative maximum at x equals x0, right? So again, if the first derivative evaluated at the point is 0, and the second derivative evaluated at the point is a negative number, then there is no other possibility for this function. It has to have a nice smooth peak, and that peak again is due to the fact that the function will be concave down, right? Then unfortunately there are instances where this test does not lead to a definitive conclusion, right? So unfortunately, if we plug the critical number or value into our second derivative, and if that is also equal to 0, then it's inconclusive. We don't know what's going on, right? So there's not enough information based on this evidence for us to come up with a definitive answer. So we basically say, well, in fact, let me say this. Let me add two more things. If the second derivative is at that point is equal to 0, or the second derivative evaluated at or evaluated at x, if that is undefined, right? No conclusion can be made, right? So the test is inconclusive. And it means we have no idea, lots of things could be going on, but there's nothing that we can say for sure has to happen. That's not the case when we get either a positive or a negative number. We get a definitive answer there, but if the second derivative happens to be equal to 0 as well, then lots of different things could happen, all right? And that's our second derivative test. So let's do a couple examples, see how this plays out. All right. So let's see. Let's start with number 1, and let's start with a polynomial. We love our polynomials. So f of x is equal to 4x cubed plus 7x squared minus 10x plus 8. And let's say, so this is our function. Let's say the instructions would be, so find all critical values of f of x, and if possible, use the second derivative test to classify them, right? So use the second derivative test to classify. All right, so the thing with the second derivative test now, we're not going to use a number line, right? We start with our first derivative and find our critical values the same way. It's just that now, instead of drawing a number line and doing test points, we're going to find a second derivative and plug in those critical values. And hopefully we'll get something either positive or negative, because if we don't, right, then again, we can't say what we won't be able to give an answer, right? Okay, so first step, as always, let's look at our critical values, see what we can find. All right, so for our critical values, we need our first derivative, and that is 12x squared plus 14x minus 10, right? Now, because this is a polynomial, right, again, we know that polynomials are always continuous, they're always differentiable. So I don't even have to worry about, I'll state it, but that this derivative will always exist. So the only critical values will occur when our first derivative is equal to 0. So we're asking ourselves this question: for what values of x is my derivative equal to 0? Well, it's another quadratic, so let's see if we can solve this quadratic. So we have 12x squared plus 14x minus 10 equals 0. Notice I could divide through by 2, so I could get 6x squared plus 7x minus 5 equals 0. And now I'm looking for factors of negative 30 that add to give 7, right? A positive 7. So we could do something like this. I'll show you the standard way of factoring. So write this 7x as plus 10x minus 3x and then minus 5 is equal to 0. And then you factor by grouping, right? So out of the first pair, in fact, let me write the grouping. So it looks like that. And then I'll do that. Out of the first pair, factor out a 2x, and then that leaves 3x plus 5. Out of the second pair, factor out a negative 1, and then that leaves, again, 3x plus 5. And whenever you see that, you know, yep, I'm on the right track. Factor again. So take out a quantity, 3x plus 5. That leaves a quantity, 2x minus 1. Right? So we can look at this, so we can see we have our two critical values. Either x is negative 5/3 or x is positive 1/2. All right. So now, as far as classifying, at this point when we were doing the first derivative test, we would now, draw our number line and pick test points and check to see whether the first derivative changes from positive to negative. We're not going to do that. What we're going to do now is use the second derivative, right? So to classify, so we're now going to classify based on f double prime of x, right? So that means we have to find f double prime of x. Now, let me scroll back up just a little bit. Here is f prime. So let's differentiate this to get f double prime. So f double prime of x is 24x plus 14, right? And again, and what the second derivative test says now, if I take my critical value, negative 5/3, and if I plug it into this function, and I get something positive, then it means at this value of x, the function has to have a relative min. If I plug it in and I get something negative, right, then at that point the function has to have, f of x has to have a relative max. So let's go ahead and evaluate it, right? So f double prime of negative 5/3. So we have 24 times negative 5/3 plus 14. So negative 5/3 times 24, so that's a negative 40 plus 14. Oh, that's a negative 26. So we got a negative number. So let's kind of, put a little sketch together to illustrate what this is going on. So at negative 5/3, we have a stationary point. So we know it has to be either like this or like this, right? It can't be any sharp corners, or actually it could look like this as well, right? Or like that, right? But now, because the second derivative is negative, then it means the function has to be concave down. So it rules out immediately these other three options can't be any of these, right? Because again, we have a stationary point and the function is concave down. The function is concave down because the second derivative at that point is negative, right? So the only conclusion is that at x equals negative 5/3, f of x has a relative maximum, right? So let's write that down. So at x equals negative 5/3, our original function f of x has a relative maximum, right? And again, it's based on these two things: stationary point, concave down, right? No other possibility. Well, let's do the same for the other critical value. See what happens there. Let's take our second derivative and evaluate it at 1/2. And I think you can see that we're going to end up with something positive, right? If you look at the operations that are involved, look, we have 24 times a positive number, so that's something positive, plus another positive number, so it's something positive. If you want to write down the actual number, it is 1/2 of 24, that's 12, plus 14, that's 26. So we get something positive, right? So again, the only possibility is this. Oh, concave up now because we have a second derivative that's positive, and it has to be a nice smooth low point or valley because it corresponds to a stationary point, right? So the conclusion is at x equals 1/2, our function f of x has a relative minimum, right? So I would say that this second derivative test, it's rather efficient, especially if it's fairly easy to compute the second derivative. See, like if your second derivative is going to be a mess, right? It might not be the most efficient thing. Maybe it would be easier to just use our number line approach and apply the first derivative test. But really, in general, you have a choice. You have two methods now of classifying these relative extrema. You find them the same way, right? It's all based on whether the first derivative is equal to 0 or the first derivative does not exist. Is how you distinguish between them that's different. And the distinguishing feature now is the fact that we're using concavity as a way to classify our critical values. All right, and that's it. So that's a wrap on our second derivative test, and we'll continue with our curve analysis. I'll see you in the next video.